Um, Hello, everyone. This is Samet. I work at Intel Edge Computing Group, mainly working on edge applications. So I'm trying to come up with AI models that are as efficient as possible so we can run them on edge deployment. For the first two talks, amazing talks, they were mainly focusing on the robotic side of things. In my talk, I'll mainly concentrate on the manufacturing, visual inspection, and that sort of stuff, and mainly talk about anomaly detection and Anomalib in general. So before I start going into details, maybe we can start with the challenges of manual inspection. I mean, as we can imagine, this is traditionally done by human operators. It's tedious, inconsistent, it's prone to error, and it depends on the performance of the human operator as well. Some of them are super experienced, some of them are new to the job. Even for the super experienced ones, due to the nature of the repetition, the repetitive task, they might get bored, or they might have some, urgencies, or exhaustion and stuff like that. So overall, this causes some serious issues. And when the cost of failure, I mean, even small defects can lead to serious issues. Like I think about in the healthcare, it can cause a really serious issue. I think about like an airplane parts, even a small defect that a human operator misses. Yeah, it could be fatal. Well, the proposed solution, of course, it's been used in industry nowadays. Vision AI, it provides real-time and accurate results that can help human operators. We're not here to replace human operators, just to help them reduce the error rates. And how it is done, mostly in industry these days, it's basically anomaly detection. And for those who are not familiar with the concept, is to detect unusual or irregular patterns in images and video streams. And if we talk about the traditional vision, downstream vision tasks like object detection or segmentation, those tasks usually focus on the known objects, like say object A, B, C, D, and train a model and detect them. Um, on the other hand, anomaly detection first finds what is normal and tries to identify what is not normal based on what it learns and what it knows about the normality. And it's currently being used in automated inspection, like in advanced manufacturing. So I want to show this with demo because this demo was created by Paula. She created this some time ago to demonstrate how this can be utilized in a real world setting. Um, well, I mean, there are a bunch of videos that we can show from the factory floor, but there are some license issues. So I can show this as a representative. So there's a conveyor belt and a robotic arm, and the model, there's an anomaly detection model that the Paula trained on normal data. So normal data, I mean like non-defective samples. And based on what the model learns about the normality, it can find out the defective sample. So in this case, this is the circle on the side of the cube. So this is a defective one, and the robot can pick it up from the conveyor belt. So we always have, we ensure the quality. And this is sort of how it's used in industry right now. And this is a representative example. Right. In terms of the market size, in terms of the vision applications, um, anomaly detection is one of the most widely used vision tasks following object detection. And when we look at the market value and the business value, there's a tremendous growth, a projected growth as well. That's why we're focusing on this anomaly detection problem. And the way how we're trying to tackle this problem is we create this Anomalib, which is a library to design, develop, and deploy vision anomaly detection algorithms. For those who are not familiar with Anomalib, is basically it provides state-of-the-art anomaly detection models and tasks. So users can just pick some models off the shelf and use it for their own problems. Or it also has a modular API if you would like to customize the existing models, or if you would like to start from scratch to design a new anomaly detection models. So it's there. Also, there is a command line interface that's fully configurable for end-to-end machine learning lifecycle. So if you would like to use a terminal. Finally, it provides deployment capabilities as well. So once you're done with training and testing, it is possible to choose the preference your preferred model and inference interface and use it in the real-time deployment. Right, so let me show you an end-to-end example that how it looks like. So let's say you can import an MVTech data set, which is one of the most important benchmarks in the literature. So you can choose, you can import a patch score model, which is one of the state-of-the-art models right now, and also an Anomalib engine. You can instantiate these as easy as this with the default arguments, but you can also customize these. And then you can just train the model by passing the data module and the model to the engine. And finally, you can just predict for the inference. For those who would like to prefer command line interface, there is a one-to-one mapping that's possible. So you can just do anomaly train and pass the data and pass the model, and you can train the model. Or if you would like to override some of the arguments, you can do that by just providing the category transistor in this case. But yeah, it's possible for any other components like model, engine, and so on. So this works fine, but as I highlighted in the summary of my talk, but when we train the models and deploy them at the edge, there are some certain steps that we would like to integrate, like pre-processing, post-processing, and these are kind of getting quite complicated as the models are becoming more complex and the pipelines are becoming complex. So we had to reimagine and rebuild Anomalib, and that's why we released V2, which I'm going to be talking about next. So we wanted to make it as configurable as possible. So in addition to the model-specific operations, the users will be able to provide some custom operations, which I'm going to be talking about as an example in the next slides. But we wanted to keep it as modular as possible so we can use the components across the different models without introducing any boilerplate code. And we wanted to make it as independent as possible so you don't share information between different components. Like, let's say you have an input size that you need to pass it to the data set and the model. But, this is a bit tedious, so we don't want that. So we just want no information sharing between components, no duplication. And also we wanted to have the multi-GPU enabled with different strategies. To enable these, we wanted to revisit the model workflow so that, once we have the data, we pre-process the data, apply the transforms and additional pre-processing steps, and then we pass it to the model forward pass, right? Once we have the model forward pass and the predictions, the raw predictions, there is this post-processing stage. And finally, we evaluate the results and visualize these results. So this is a standard typical pipeline for many downstream vision tasks, right? And most of the time, the model implementations in many frameworks just focuses on this model forward pass, and these pre-processing and post-processing stages are kind of excluded from this. And this becomes a problem when it comes to the deployment stage, that we need to re-implement all these pre-processing and post-processing stages. So we call these auxiliary components. With that in mind, we wanted to scope this new V2 design by having a pre-processing, post-processing, and all these components in mind, so we can have a modular API for this. So with this in mind, we wanted to introduce a submodule and a callback design. So we designed this V2 in a way that so each type of auxiliary operation, like pre-processing, post-processing, so they would be represented by a separate entity. So that they would have a separate class, and so they would be a self-contained Python class. And we would store them as an attribute in the Lightning model. So when we export the model into for a real world deployment, so they would be part of the model graph, which I'm going to be showing. So for example, if you have a model, so each instance that can be passed to the model. So let's say you have a preprocessor, and that would be a class of on its own, post-processor as well. So these a model can have a default value for each algorithm, like think about PatchCore or PATM or EfficientAD, any state-of-the-art anomaly detection algorithm. So they can have their own default preprocessor, or user can provide their own customized preprocessor and post-processor stuff. So everything super modular. And Lightning model would automatically adds it to the list of callbacks. So everything would be part of the model graph. So let me talk about the pre-processing, for example. So we have this callback and NN module design. A callback inheritance would apply different transforms in different stages of the pipeline. So what do I mean by this? So basically, when you start the training batch, you apply the train transform. When you start the validation batch, you apply the validation transform. When you start the test batch, you apply the test transform. So like every stage of the pipeline, you can apply different transforms. And NN module from Torch would include user-specified transforms in the state dictionary like this. So that would mean that it would be submodule of the Lightning. So when it comes to exporting the model for inference, everything would be wrapped in the model graph. So you don't need to recreate those pre-processing again. So let me show you as an example. So let's say we import our torch vision transforms like normalization, resize, and any other transform you want to do, and an import engine, PatchCore, and a preprocessor class. So we can create the preprocessor class by instantiating these transforms and passing here. And this preprocessor class can be passed into the PatchCore model or any other model that we have. Then we can train the model by passing this model here. So we had a train model. Once we export the model for deployment, let's say an ONNX model in this case, or OpenVINO or TensorRT, we don't need to do any manual pre-processing anymore, because all these transforms and the pre-processing operations would be within the model graph. So this means that when we load the deployed model, let's say an ONNX model in this case, we can just import a raw image and pass the raw image into the model, and we can get the predictions, and that's it. So we can get rid of this normalization, pre-processing, and all these operations within the deployment stage, because everything is in the model graph. Post-processing would be the same. So for the callback here, we would collect the statistics during validation and training, like normalization statistics, thresholding statistics, and so on. And we would apply post-processing operations during training and predicting. So let's say on validation batch end, so every single batch during the validation, we would update the threshold, we would collect the normalization statistics, and during the epoch end, basically you would compute the threshold and the normalization stats. For the NN module, again, the same logic. We would merge that into the model graph. So when we deploy the model, we would have all these thresholding and normalization, all these statistics. So we could use off the shelf. So we don't need to recreate them, or we don't need any metadata or anything. Let me show you an example. So let's create an engine, PatchCore, and the post-processor classes, and have a customized post-processor class. Again, if you don't have a post-processor class that we define as a user, PatchCore would use its own post-processor class. That's the default one. When we look at the model.postprocessor, we would see like all the image thresholds, pixel thresholds, image normalization statistics, and so on. When we train the model, the export the model, again, on X in this case, we would have the post-processing included. So what we need is we would just load the deployed model and pass the raw image into the model, and we would get the predicted predictions, and all these predictions would be post-processor applied. So we could just use them as is. So anomaly map would be post-processed, predicted scores, predicted labels, predicted mask, everything would be post-processed, so we could just use them off the shelf. For the evaluation part, again, it's the same logic. So we can update and compute different metrics in different stages of the pipeline. So let's say on validation batch end, we would update the validation metrics. On test batch end, we would update the test metrics. And when epoch end, we can just log these. This is how we would like. For an example, so we can import some metrics like AU rock or F1 score. And for a basic usage, we can create an F1 score. The fields would be predicted labels and the ground truth labels. And let's create an AU rock metric with, again, predicted score and the ground truth label. So these would be the image level metrics, like classification metrics. And a create evaluator, like a test metrics, like F1 score and AU rock. If you want to have state-specific metrics, like let's say different metrics for validation, like AU rock and F1 score, but for test metric, we would have more comprehensive. So we would have like image level metrics and pixel level metrics, so it's possible. And we can customize this by passing these validation and test-specific metrics to the evaluator. And then update the model with this evaluator, and everything will be logged accordingly. We also have this visualizer that we can customize. So we can apply visualization at the end of the batch or end of epoch, and we can have a different strategy between image and videos. So something like this. Let me show you an example. So let's say we want to use a default image visualizer. We can just import it like this and pass it to the model. And this would give us something like this. So for those who are familiar with MVTech dataset, you can have the default view. But if you would like to customize the visualizer, say like, you want these fields, image, ground truth mask, anomaly map, and if you would like to overlay fields like anomaly map on image, so you can have this. So you have the image, ground truth mask, anomaly map, and if you would like to customize, the overlay ones, so overlay anomaly map on top of the image, so you would get this view. So let's say we want to customize a little bit more. When we overlay the fields for the predicted mask, we want this alpha color and fill. So we would get something like this with 0.7 alpha, and we filled it instead of a contour, and that would be possible. Or like if you want like a full advanced functionality, like, customize everything, that would be possible as well. So like you would get something like this. So it's fully customizable. Like overall, the advantages be like, we would have a super modular API, so we can configure each entity, reduce the number of args and configs. We would be flexible, like all these auxiliary operations, like pre-processing, post-processing, visualization are fully customizable. And model implementations can contain default operations. So if you don't want to bother with any of these auxiliary operations, and just import the model. So you can still use the default operations that are reported in the paper. And also, most importantly, everything will be saved within the model. So when you export the model to use on a real-world setting, that would be possible within the model graph. So these I kind of highlighted what's new in the API, but in terms of the new features, we also introduced several features like datasets, models, new metrics, new hardware support that maybe I can briefly talk about. So we added new datasets that are becoming kind of de facto public benchmarks. So, there are new data sets coming every day. So MVTech2 is one of them. It's a really challenging real world data set with with an additional unseen test set with some perturbations. This makes the anomaly detection benchmarks really challenging these days. Even one of the best performing models on the MVTech1, their performance on MVTech2 is really low, like 50% range, 60% range. So we have NVTech Loco added as well, MPDD, Real IAD, a multi-view data set, a VAD data set from Valeo. I think and tomorrow in one of the talks, Imira and one of the speakers will talk about this more in detail. And for those who would like a customized tabular data set, we add that support as well. So if you have a CSV file or a pandas, polars, that will be possible to customize your data set and use in Anomalib training. So we added new models from CVPR 25 that are achieving state-of-the-art results like Anomaly and Uninet. Uninet actually is the top performing model on across the many benchmarks right now. We also added some clever algorithms like Super SimpleNet and FUAS for video anomaly detection as well. We added new metrics like PMO, AUPMO, PG, and PB, I think some of which will be discussed by Imira tomorrow as well, for those who are interested. For hardware features, we added multi-GPU. So if you have multiple GPUs that you would like to train anomaly detection models, that would be possible. Also, more recently, we added Intel GPU and iGPU support with a considerably a price performance range. Intel GPUs provide a really a comparable or superior performance compared to the competitors. So yeah, if you would like to try it, you can try. Right. So I will show an end-to-end example. So how you can start with a custom data and train a model and export a model with few lines of code, and also show a really basic simulation environment, and then how Anomalib can be trained within seconds, and then perform an inference. So again, you can import the required modules. In this case, we want to do a custom data because we have a custom our own private data. So we can use folder data and import patch core and engine, initialize these classes, and train the model by passing the model and data module. This is how we train a model with one-liner and do the prediction with one-liner again. And here, note that we don't do any optimization. We can potentially do model optimization to improve the performance on real-world settings, like quantization and others. You can have much faster inference, but we haven't done that. We just show a one-liner prediction on the torch model. So let me show you a quick example how we can quickly have a simulator that mimics a factory floor on a conveyor belt. You have a camera on top. This is a pretty standard manufacturing quality inspection use case that we have quite a lot of real world use cases, but this is just a simulation. So here we collect some data based on the spawns. These are the only normal examples, so non-defective ones. We just captured 10 images, as few as 10. And as you can see, the training starts quickly. And within a few seconds, we finish training. And as you can see, we have a train model already, and it picks up the normal images. So we don't have any anomalous samples yet. Now I can create some anomalous samples here. Yeah, it's still normal, but as soon as passing some anomalous samples, we can the model. Yeah, as you can see, there's an anomalous sample here, and it's picked up as an anomaly. So this is like This shows how you can quickly capture the data and train a model within seconds, and train an anomaly detection model that might be deployable. And note that in the previous example, I showed the code. I didn't do any optimization, so this is 11 frame per second. But if we had some optimization like Onyx or OpenVINO, this can easily be increased up to 30 plus frame per second. In some models like Pattern, we even have 100 plus frame per second, which is a amazing FPS for a real world use case. Yeah, so this overall can show that within a few lines of code, you can start with nothing and collect data and train an anomaly detection model and deploy it for a real world use case.